Let's talk about another common problem in probability, especially in computer science. That is the so-called balls and bins problem. The idea here is that we have some number of bins, say these 10 bins, buckets, trash cans, holes in the ground, whatever, and we're going to throw 20 balls into these bins. We're going to assume the balls always land in one of the 10 bins and that there's a uniform chance it lands in any of the 10 buckets. And, well, let's see it out. So I throw my first ball and it lands in 5. So my next one, 6. My next one, bin 2, 6 again, 8, 3, and so forth. And I keep throwing the balls over and over until I get to number 20. There we go. So that's my 20th and final ball. It's golden in color, so I know when to stop. And that's the problem. So something I find really helpful to do when you're approaching a new probability space and you're learning probability is to say, how does this fit into the definition of random experiment? That is, what's the K? What's the N? What's the size of the sample space? Is this with or without replacement? And is this a uniform probability space? So, question for you. What is it? You don't have to do this one if you don't want. I mean, you never have to. But I'll spoil it if you want. But I do think it is a good exercise to make sure you really understand the definitions. Okay, first, let's talk about K. K is the number of samples we're drawing. It's going to be 20. What are we drawing? Well, we're drawing bin numbers. So N is 10. Those are the possible outcomes. Each individual sample you draw is some number between 1 and 10. It's with replacement because you get the same number multiple times. So it's not you can only get bin 2 a single time. The sample space, because we're drawing with replacement, there's 10 to the 20th possibilities, just as before, with any drawing with replacement. And lastly, the probability space is uniform. So in other words, that specific distribution of balls above, I mean, ignoring the fact that some of them are sitting on top of each other and one of them's a different color. If you just say how many balls are in each bin, this specific distribution I got of 2, 5, 1, 3, 2, 2, 0, 2, 3, 0, that happens 1 out of 10 to the 20th times. Okay, so that's the balls and bins problem. So let's try and do some reasoning on this. Now I'm going to put the size of the sample space in a slightly blue color, for those of you who can see the color blue, and that will help a little bit in keeping track of arguments in a bit. So a question we might ask ourselves is, what is the probability that the first bin is empty? So that the question is, what's the probability that this first bin just has no ball in it? How do I do that? Maybe think about it. Well, since all of the outcomes are equally likely, it's a uniform probability space, we just need to count the number of outcomes where no ball lands in bin 1. Okay? So how do we do that? Well, this is similar to other problems we did before. We're going to assume that all the balls landed in the other bins, 2 through 20, and we say, well, how many such outcomes are there? Okay, well, how many different ways are there for 20 balls to land in 9 bins? 9 to the 20th possibilities, right? This is, you can think of it as sampling with replacement. We're only allowed to use 9 of the bins. So it's 9 to the 20th rather than 10 to the 20th. So the probability that the first bin is empty is simply 9 to the 20th over 10 to the 20th, which is about 12%. Okay? It's a nice argument. It's pretty straightforward, at least if you're comfortable with the counting problem. Okay? All right, so that's a probability that bin 1 has no ball. What about the probability that bin 1 is not empty? That is, that it has at least 1 ball. Well, that can be a little more challenging if you try to approach it in the exact same way. Like we can't just say, oh, well, imagine a slightly smaller problem with only 9 bins. How many are there versus the 10 bin case? In this case, we need to do something a little more clever. And this is a very common thing to do in probability, which is to say, well, the probability that bin 1 is not empty is just 1 minus the probability that it's empty, right? We could just say 1 minus the other thing. So in other words, there's a 12% chance that the first bin has no ball, which means there's an 88% chance that there is at least 1 ball. Okay? And this is a thing we'll have this is a technique that we'll use over and over in doing probabilistic reasoning, which is to observe that for an event A, the probability of that event is just 1 minus the probability of not that event. Okay? So let's generalize in a couple of ways. The first way is, let's consider an arbitrary number of balls M and an arbitrary number of bins N. Okay? I mean, we're going to assume as before that every ball is equally likely to land in the n bins. So in this case, k is m, n is n. We're sampling with replacement, and the size of the sample space is n to the m. Okay? Because before, when there were 20 balls and 10 bins, it was 10 to the 20th. So it's n to the m. All right. So question, what's the probability that bin 1 has no ball? Well, we can do this by direct analogy to before. So for the k equals 20, n equals 10 case, we just said it was 9 to the 20th over 10 to the 20th. Okay. So if k is some arbitrary constant m, and n is some arbitrary constant n, then we just have the same idea. We have n minus 1 to the m. That's the number of ways that m balls can land in n minus 1 bins, because we're basically imagining a slightly smaller problem where there's one less bin. And we're just dividing the size of that problem for n minus 1 bins by the size of the problem for n. Okay? So we end up with n minus 1 to the m over n to the m. Now we can simplify this expression somewhat by saying, okay, well, let's bring everything together under one exponentiation to the mth power, right? So n minus 1 over n to the m. And then we can, if you'd like, write it as 1 minus 1 over n to the m. Okay, so that's a function that tells us the probability that bin 1 has no ball. Likewise, I mean, that's a probability that any particular bin has no ball. There's nothing special about it being bin 1, but this is a formula. So why does this formula matter? I mean, it's kind of interesting to derive, but you'll also see it used occasionally in practice. So for example, in computer science, you might say, okay, well, imagine we send m jobs to one of n servers randomly. We're not doing any like load balancing. We're just sending them out there. The question is, well, how likely is it that server 1 is not used? And it's that expression, 1 minus 1 over n, all to the m. Or likewise, imagine you're modeling hash tables from CS71B, or whatever data structures class you might have taken. In this case, you might say, what's the chance that the first bucket doesn't get used if the items are spread uniformly across hash table buckets? Well, it turns out to be 1 minus 1 over n to the m. Okay, that's one way in which we'll generalize. We derived a nice form. Let's talk about the relationship now between the buckets and balls problem and the dice problem and the coins problem. Okay? So it turns out that some of our previous problems are related to the buckets and balls problem. So imagine the problem of rolling a 4-sided die twice. I claim that's actually the same thing as the buckets and balls problem. You have to think pretty carefully, but what would m and n be if we're thinking about this idea of rolling a 4-sided die twice? Okay, so this is the process of throwing 2 balls into one of 4 buckets. So 2 balls, 4 buckets. Okay. How about flipping a coin 16 times? Okay. So in this case, you have 2 different bins you can land in, and you're going to do 16 ball throws. So m equals 16, n equals 10. So both of those problems actually are really this buckets and balls problem in disguise. Here we have drawing a hand of 5 cards from a deck of 52 cards. What about this one? Well, it turns out this one is a trick question. You might have had a hint from the fact the title didn't include cards. And that's because with cards, drawing a hand was without replacement. So it doesn't match the independent ball throwing. In particular, those lines of reasoning like, well, I mean, it's a totally different problem, right? I mean, because you can't get the same thing twice. That's just fundamentally different than being able to throw into the same bin. That would be the equivalent of every time a ball lands in a bin, it explodes. That's the drawing a hand of 5 cards from a deck of 52 cards problem. Okay. All right, that's buckets and balls.